Okay, now we're going to look at a section called mathematical induction. It's a way of proving that certain things are true. Basically, it requires two steps. First, you prove a base case. Usually the base case is for when n equals 1. In other words, like the very first term in a series. And then you prove that if the kth case is true, in other words, that's an assumption that it is true, then you show that the kth plus 1 case will also be true. This second step is called the induction step. And so part of what's going on in this section is we want to show mathematical induction, and then the other part is we're going to show why some of those relationships that I showed you earlier in the chapter are true, such as this proof that we're going to look at right now, which is that the sum of 1, 2, 3 up to n, in other words, a problem like the sum of 50 consecutive numbers equals n times n plus 1 over 2 for every positive integer n. So first we want to show the base case, in other words, n equals 1. So if we plug in a 1 everywhere we had in n, we would have 1 equals, because of course 1 is the very first value. So 1 equals 1 times 1 plus 1 over 2. Of course 1 plus 1 is 2, 2 over 2 is 1, and so yes, 1 equals 1. Next we want to show that if the kth case is true, then the kth plus 1 case has to also be true. Or at least that's the induction step to prove that. So first off, if we use k for some number of n, so it's just a generalization of what n is, note that 1, 2, 3, 4 up to k, then that needs to equal k times k plus 1 over 2. In other words, we're just using what we had right up there. So we're assuming that to be true. Now we're going to go to the kth plus 1 term. So we're going to add that to both sides. So on this side, we have 1, 2, 3, dot, 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 plus k plus 1. Over here, we're going to take what we had, the k times k plus 1 over 2, and add k plus 1. So since this is true, then adding k plus 1 to both sides would have to be true as well. Now, with a little rearranging of the right side of things, note that here we have k plus 1, here we have another k plus 1, so we could factor out the k plus 1, and we would have k plus 1 times the quantity k over 2 plus 1, which is what we have right there. And then that could be arranged because, of course, this is a fraction, and we want to add it to the number 1. We can call the 1 2 over 2, and so now this expression would be k plus 1 times k plus 2 over 2. However, if we looked at this and split apart the 2, we would have k plus 1 times the quantity k plus 1 plus 1 all over 2, which is just what you would have gotten in our original expression if everywhere we had an n, we had put in k plus 1. So again, note that the last expression is what you would have gotten if you had put in k plus 1 for n, since it has been shown that if s sub k is true, s sub k plus 1 was also true. The statement for Sn is true for every possible integer value of n. So, two steps. First, assume the base case, and then second, the k plus 1 case. Now, we want to let Sn, this should be a subscript, but Sn represent the given statement. Use mathematical induction to prove that Sn is true for every positive integer n by verifying S1 and then writing Sk and Sk plus 1, and then using algebra to change Sk to Sk plus 1. Finally, write a conclusion based on the previous step. So, let's look at this first problem, where we have 5, 10, 15, 20, so forth, up to 5n. And we want to say that that equals 5n times n plus 1 over 2. So first off, let's look at the base case. S1 will equal 5. Okay, that's that one right there. And so if we use our formula, we would have 5 times 1 times 1 plus 1 all over 2. Of course, this is just going to give me 1 plus 1, which is 2. 2 over 2 is 1. 5 times 1, as I say, we're going to have 2 over 2, which is just 5. So it did work. Check. Okay, now let's write out the assumption step, SK. So SK, well, that's going to be 5 plus 10 plus 15 plus dot 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 up to 5k. So wherever we had an n, we now have a k, and that should equal then 5k times k plus 1, and then all of that over 2. And so this is assumed to be true. So there is our assumption step. Alright, so now we want to show, and this isn't exactly a step, it's just, you know, what we're trying to do here. We want to show that sk plus 1 is going to equal 5 times k plus 1 times k plus 1 plus 1 all over 2. We want to show that that is also true. So we already have our sk up here, so we're going to say then that sk plus 1 will equal 5 plus 10 plus 15 plus dot 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 plus 5k. Still have what I had before, but now we're going to add the 5k plus 1, and of course that's got to equal what was on the other side here, which is we have 5k times k plus 1 over 2 plus 5k plus 1. So we just took what was up here, and then we added the 5k plus 1 to both sides. So now we got to do our rearranging. So the sk plus 1, well, that's going to equal, and we're looking at this part right here, that has a k plus 1, that has a k plus 1, so we can factor out the k plus 1. And what we have left, well, here I have 5k over 2, and here I would have the 5. Now I could have done this already, but these both have 5 in it, so I can take out the 5. So let me go ahead and do that. 5k plus 1. And then on the inside, I still have the k over 2 plus 1. Note how this is very similar to what we had before. So that is 5k plus 1. And then we have k plus 2 over 2. Because the 1 will be 2 over 2, so that they have the same denominator, I can put them together. And finally, separating the 2, I have 5 times k plus 1. And then I have k plus 1 plus 1 all over 2. And so you can see that I have in fact shown what I wanted to show. Here's my 5k plus 1, the k plus 1 plus 1, all over 2. Okay, and so, if you will, sk plus 1 equals 5k plus 1 times k plus 1 plus 1 all over 2. And so we have done mathematical induction. All right, a second example. This one deals with the formula for the summation of cubes, 1 cube plus 2 cube plus 3 cube up to n cube. And that's to equal n squared times n plus 1 squared all over 4. So again, let us look at the base case. So S1, which is supposed to equal 1 cubed, because that's our first term. So that's supposed to equal, then we've got 1 squared, 1 plus 1 squared, all over 4. And of course, this is 1 and 1, which is 2 squared. And so I have 1 times 4 over 4, which of course is just 1. So I have shown that the base case is true. So now we're going to assume the SK case, which will be 1 cubed plus 2 cubed plus 3 cubed plus dot 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 plus k cubed equals k squared, k plus 1 squared all over 4 is also true. So we're going to assume that. So we want to, and again, this is not really a step, it's just explaining what I want to do. I want to show that sk plus 1, which would be again 1 cubed plus 2 cubed plus 3 cubed plus dot 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 up to k plus 1 cubed, that all of that will equal k plus 1 squared times k plus 1 plus 1 squared over 4. So just as we did before, we're going to start off with this and add the k plus 1 cubed to both sides. So that'll give us, let's see, we're going to have s k plus 1 equal to 1 squared plus 2 squared, or cubed, excuse me, plus 3 cubed plus dot 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 plus k cubed plus, and here's where we're adding in the k plus 1, k plus 1 cubed equal, and again we're taking this part here, k squared, k plus 1 squared over 4 plus k plus 1 cubed. So we have added the k plus 1 cubed here and here. So now I have the sk plus 1, and we're going to do some algebra on this part over here. Okay, so we have a k plus 1 squared here. Now here I have k plus 1 cubed, but I can pull out a k plus 1 squared from that, and so that would give me a k plus 1 squared, and then the rest of it, well, here I still have k squared over 4, and then over here I would have a k plus 1. Again, pulled out the k plus 1 squared right there, and here I pulled out 2 of the 3, so I left one of them behind. Now if we go ahead and put all of this together, so in other words, I'm going to need to multiply this by 4 over 4 so that I can put it all together. So I still have the k plus 1 squared here, and then this, I'll just go ahead, k squared over 4, and then the other part will be 4 times k plus 1 over 4. So by doing that, now I can add these two together, and so this is going to give me k plus 1 squared, and then I have k squared plus 4k plus 4, and then all of that is over 4. Okay. So I'm going to go ahead and just rewrite it the way it is without changing anything. So k plus 1 squared, and then I have k squared plus 4k plus 4, and then all of that is over 4. So again, I just copied all of that down here so that it's easier to follow. Now it turns out that this part is factorable. So we still have our k plus 1 squared, but now in here, that is actually k plus 2 squared. And then I can separate it, and so I still have my k plus 1 squared, but now this part I'm going to make, I'll use this again. This part will have k plus 1 plus 1. So what was k plus 2 quantity squared is now k plus 1 plus 1 quantity squared, and then it's still all over 4. And this is what we wanted to show. Because we ended up with sk plus 1 equals k plus 1 squared times k plus 1 plus 1 squared over 4. Okay, and again, if we look back here, that's what we wanted to show. Here's our k plus 1 squared, k plus 1 quantity squared, and all over 4. All right, so something just kind of like for the fun of it. I realize that most people wouldn't necessarily think this was fun, but it is an interesting little item here. So what we have is what's called the Coach Snowflake. And we're going to do a particular kind of operation. So you start off with an equilateral triangle in which each side is 1. And then basically what happens is the middle third, you eliminate that part of the line, and then you put in what would have been an equivalent equilateral triangle where that existed. So in other words, the lines were there. Okay, that's where the lines were, but we got rid of that middle third and then created another triangle which is smaller. And then each of these sides, we then again took the middle third and put another triangle in there. And this is called, basically, this is what fractals are. So it says find the number of sides of the nth figure of the snowflake, and then it says find the first 5 terms for the perimeter of the Coach Snowflake. So let's take a look. First off, when n was 1, we had 3 sides. And of course each one is a length of 1. When n is 2, okay, so here this is our second one. So n is 2. Well, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We now have 12 sides. When n is 3, we have 48 sides. And when n is 4, we have 192 sides. Now, at the same time, each of those sides is getting smaller. So here, each one was a 1, but here, each one of these is a 1/3. And then you go 1/3 of 1/3, so each one of these would be a 1/9, and then 1/27, and so forth. All right, so we've got n equals 1, 2, 3, 4, and we have 3 sides, 12 sides, 48 sides, and each side is exactly the same size of the figure. The sides are getting smaller and smaller. So we need a pattern for 3, 12, 48, and 192. Well, of course, 3 is 3 times 1, and 12 is 3 times 4, and 48 is 3 times 16. As I've mentioned before, when you're trying to find patterns, one of the things to start with is there a common factor? And 3 and 12 and 48 all have a factor of 3. And 192 does as well. And then I notice that, well, this is 4, this is 16, which is 4 times 4, and it turns out that this one is 3 times 64, which is 4 times 4 times 4. And so now I can, just because I recognize that they all divisible by 3, a second pattern has shown up. And this one basically is 3 times 4 to the 0. This one is 3 times 4 to the 1. This one is 3 times 4 squared. And this one is 3 times 4 cubed. And so I have found a relationship that increments 0, 1, 2, 3, and so forth. So from that, I can see that the number of sides in this case will be 3 times 4 to the n minus 1. And I'm just using the multiply there. It's not 3x, it's 3 times. 3 times 4 to the n minus 1, because notice the exponents, that was for n is 4, n is 3, and so forth. Now, so that's for how many sides there are. Now, in addition, we can look at our perimeter. So for n equals 1, well, P1 was 3, because 1 and 1 and 1, it's an equilateral triangle, all the sides are equal. For n equals 2, P2 equals, well, 3, but now each side actually has 4 sides to it, or what was one side here, note that here it's 1, 2, 3, 4, so it's actually, and then there's 3 of those, it's actually 3 times 4/3. Where n is 3, we've got, so now you've done the same thing, and this is our P3 now. Okay, so here I've got, you know, boy, there's a lot of sides there. There's going to be 48, but each one of them is 1/9. For the n equals 4, and by the way, 3 times 4, that gave me my 12 sides, by the way, so I could have done that, but 3 times 4 is 12 over 3, each one's 1/3 of what it was. For n equals 4, I had my 192 sides, so P4 is 192 sides, but now each one of those is 1/9, or actually, no, excuse me, over 27. We got to keep going by 3s. And if I wanted to, I didn't have that figure, but if I was going to N5, P5 would equal, now again, it's 3 times 4 to the 1 less, and so I now need 3 times 4 to the 4th power, which would be 768. But this would be 1 over 81 in that case. So there are the perimeters. Now, we again want to maybe simplify this just a little bit. So for my P2 case here, of course, I've got the 3's will cancel, so P2 will be 4. For the n equals 3 case, I'm going to pull out a 3 that I had before, and so the P3 case will be 3, and then what's left, 3 out of the 48, that's 16. I'm getting back to that 16. So I have 16 over 9. And then the P4 case will be 3 times, and in this case it's 64 over 27. And then in the P5 case, it's 256, or 3 times 256 over 81. Now if I wanted to simplify this a little bit more, P3 of course, I can cancel out the 3 and the 9, and so that's 16 over 3. P4, again, cancel out the 3 and the 27, so that's 64 over 9. And then here the P5, that's going to be 256 over 27. So in general, my P sub n will be 3. Well, let's see what it'll be. This is P5, so it's going to be 4 to the n minus 1 over 3 to the n minus 2. So that's one way to look at what the nth term for the perimeter would be. Another way of looking at it, maybe a little bit more succinct, if we pull that 3 back out, because we had all those 3's, it would be 3 and then 4/3 to the n minus 1. So that could also be a way of writing it. So just, something to take a look at, a kind of interesting figure that has this repeating pattern where the sides get smaller and smaller and smaller, but even with something that complicated looking at the end, when we have something like this, there is a way to figure out what a general form for the perimeter would be, and therefore, we went through P5, we could go, P10 or P20, whatever, and figure out what, in fact, the fraction would be for the perimeter. And so we have section 7.5.